So our problem here is to construct optimal binary search tree from given data. Okay, so let's see what it means. So if we are given numbers w1, w2, w3 till wn, where it is in increasing order, and if the fixed probabilities of searching these numbers are p1, p2, p3 till pn, then what happens is that we have to construct a binary search tree that minimizes the access time. And we have to note that in a binary search tree, the number of comparisons that we need to do to come to an element at depth d is d plus 1. So that is quite simple. And if we see, so let's take one example. So first, what is binary search tree? So 20, 10, 30, 25 and 40, here 5 and 15. So this is an example of binary search tree. And why? Because at each node, if we see, so we see that it's basically, so 20, so its left child is less than the parent and right child is greater than the parent, and this property is followed at each of the nodes. Okay, so this is the binary search tree, and here we see that the elements are 5, 10, 15, 20, 25, 30 and 40. So these are like w1, w2, w3, w4. So these are the 7 elements, and let's say in the question we will be given some probability that, okay, when given these numbers, the probability of occurrence that we search some number, let's say 5, is 0.1, of searching w2, that is 10, is 0.05, of searching w3 is 0.22, this 0.15, something like this. We are given some probabilities of searching these numbers in the binary search tree. And what are the other things to know? This is at depth d is equal to 0, this is at depth d is equal to 1, this is at depth d is equal to 2. So when we search, let's say 25, so how many comparisons we have to make? So coming here, I have to search here, then I know that, okay, 25 is greater than this, I will search in the right subtree. Now 30 is greater than 25, so I come here, and in the third level I search. So it will be d plus 1 comparisons I have to make. And what will be the cost? Because overall it's occurring like p of I is the occurrence probability, so this will be the cost for searching this node. Okay, so this was about the BST. So now we have to construct some optimal binary search tree. So let's see this example. Okay, so if wi, so given w1, w2, w3 till wn, and if wi is placed at depth di, so we want to minimize what? So I have all the elements w1, w2 and till wn, and what I do, I sum their cost of searching. So I just do pi into 1 plus di and sum it over all the elements. Okay, so example here is, let's say I have a BST, I have given some elements like 5, 9, 12, 16, or we can take these as some words also which can be sorted, and then there is the probability of occurrence of these words. Okay, so 5 can occur 0.22 by probability, or 22% of times. 9 can occur 18% of times, something like this. And one thing more is that given these numbers, so I can construct multiple binary search trees. It's not that we can construct a unique binary tree, we can construct multiple binary trees from given numbers. So like here I can start with root node as 25. So this is our case. So what happens here? So we see is that our root node is 25 now, and here we have so a left subtree and right subtree. So I could have taken 30 also here, then 45 would have become its right child. But so we see that okay, we can construct a lot of binary search trees from given numbers. Here there is a tree starting with root node 16 and something like this. So what we see is that we can construct multiple BSTs. So our question is to construct such a BST that requires minimum cost, and where the cost is given by this. So let's see. So if we are finding the cost of this one, it will be something like here. So we will be having a depth 0 here, 1, 2 and 3. So let's see in the next slide how the cost differs. Okay, so if we calculate the cost based on the previous table, so this is d is equal to 0. So the probability of occurrence from the previous table was 0.20 and it is at depth 0. So when I come to this one, I just have to make one comparison. Then I come to depth 1. So here I have 1 plus di, so it becomes 2. So 0.22 for the 5, and here is the 25 one. So next comes, we have 3 things at level of 3 or depth of 2. So I calculate all these and it comes out that the cost, if the binary search tree is like constructed like this, so it will be 2.15. And now my question is, for all these possible constructions, I have to find the minimum possible cost. Okay, so what should be done, how to solve this problem? And here we see that we will try to form a dynamic programming solution to this problem. So what I say here, that OBST, so this OBST of I comma j, so it means that the cost for construction of optimal binary search tree from element I to element j. So here what happens, this means I have taken from elements I to element j, and there will be one root which can be the ith element, I plus 1th element, I plus 2th element, or till it can go to j. Okay, so now what I have to do, it will be something like this. I will take a root, I will have the left subtree from wi, so let wr be the root, then the left subtree will consist of wi to wr minus 1. Okay, and the right subtree will be wr plus 1 till wj. So we see that again this is kind of becoming recursive. So here again what happens, now we have to reconstruct a tree from wi to wr minus 1 with some root, and similarly here. So we at least find that okay, there is overlapping sub problem. Okay, so there is overlapping sub problem, and then we find that is there optimal substructure also. Okay, so these two define dynamic programming. So optimal substructure. Okay, so this is optimal substructure. So what it means, that the solution for the optimal solution for the binary search tree construction from node I to j will be the cost of optimal binary search tree construction for node I to node r minus 1 plus node r plus 1 to j, and with root as the rth element. So we see that it follows optimal substructure, and at the same time it follows overlapping sub problem, because there is, we see that we can have a recurrence relation kind of thing. So now we try to find how to do it. Okay, so I said that okay, when we construct a BST from node I to node j, so we can have the root as any of the j minus I elements. So I can have node I as the root, so I plus 1th element as the root. So this root R can vary from I till j, so any of them can become the root. So we have this j minus I possibilities. And so let's see now what are we doing here. So OBST I comma j represents the cost of constructing optimal binary search tree. So I have R possibility, so R varies from I till j, which means I can take any one of these elements at the root and construct the BST. And then what I say that okay, so let's WR be somewhere in between. So my left subtree will be WI to WR minus 1. So this is now OBST I to R minus 1, plus I have the cost of right subtree, that is OBST R plus 1 comma j. And then what happens? I also have PR, which is the cost of constructing the comparing the root. So that comes here. And what else comes? So other things that come is we have not considered here height, okay, or the depth of the tree. So we are considering that okay, this is the first level, but that might not be true. So what happens is that when we construct at one level, we go one level down the tree. So it means now all the elements that are below this level 1 or depth 1 or depth 0, so they have at least got one comparison. So it means what? Now whenever I try to search something below the root, so I will get the cost of occurrence of these elements. So that's why I sum from k is equal to I to R minus 1 pk. So it means these elements, when they will be searched, at least they will have one comparison made here. So that cost will be added. Similarly for the right subtree for all these elements, because they are now at least they are down by one level, so these comparisons will come. So we see, so this is the case. And now what happens? So but if we see PR, then this term and these terms, so they are basically summation k is equal to I to j pk. Okay, so this is what we can see here. And what happens now, let's see further. Okay, so this was the most important recurrence relation. We said that okay, because this problem follows optimal substructure and overlapping subproblem because of the recurrence relation and a lot of overlapping recursions. So we see that this follows. And so let's try to just make it clear. So we say that OBST I comma j is equal to minimum I is less than equal to R is less than j, and then I write, so OBST I to R minus 1, which is the left subtree, plus the root cost of the root, one comparison is needed, so that will amount to the probability for the total cost, expected cost. So it will be P of R plus OBST of R plus 1 to j, plus we have the cost, because now one root is formed, so all other elements are one level down. So I will have k is equal to I to R minus 1 pk plus s is equal to R plus 1 to j p of s. Because this is the right subtree, all the elements, so at least one time they have to be compared here in this level, one root level they have to be compared. Similarly for the left subtree. So this we see that it now becomes, we can make it precise. So this becomes OBST I comma r minus 1 plus obst r plus 1 comma j plus, so this all adds these terms, add to something like k is equal to I to j p of k. And what happens that, okay, so this r is varying from I to j, so if, and this is equal to 0 if, so this is the case for I is less than equal to j, but if I is equal to j minus 1, then this cost is 0, because it means what, I have some root, so this is the first element, it has all the right subtree, so that will happen when, so I take the r as the first element, so everything will come to the right, and then if I take r as the last element, so everything should be towards its left. So this is the recurrence relation. And now let's see, so what happens is, we have taken the problem previously discussed. So our problem was given here, that this was these are the numbers and their probability of occurrences are given. So now we construct binary search tree out of this. So let's see, so we have got some calculations. Okay, so this basically tells, so this is the, this row is the iteration, okay, how many iterations I need, and this tells that, okay, from where to where I take the element. Okay, so let's see, so this is from, so this is 1 to 1, this is 2 to 2, this is 3 to 3, 4 to 4, so something like this. And if I see here, so it will be, so this is 5 to 5, 6 to 6. This is the cost of constructing a tree with elements I and j given as this. So similarly, this is 5 to 9, so this is basically 1 to 2, this is 2 to 3, cost of 3 to 4, 4 to 5, 5 to 6, 6 to 7. So this one in the table is 1 to 3, so 5 to 7. So these are the costs. So this is 1 to 4, 2 to 5, 3 to 6, 4 to 7. Similarly, this is 1 to 5, 2 to 6, 3 to 7. This is 1 to 6, 2 to 7, and this is 1 to 7 itself. So this is a triangular matrix. It basically tells that this is, again we can see here, these are the sub problems. Okay, so these are the sub problems. So let's say for example this one 3 to 7, it means the cost of, optimal cost of constructing a binary search tree which has elements from element 3 to element 7, which is 12 to 45. Okay, so now let's try to use our algorithm for a few cases. So let's see one example. Okay, so I will take one example which will help you understand this problem. So let's take one simple example, cost of 2 to 5. So here cost, or we have written obst 2 to 5. So this will be minimum of what? So one thing is I can take, so the formula was obst, so it is I to r minus 1 plus obst r plus 1 to j plus summation k is equal to 1 to n pk. Okay, so this term will be common for all of them. So we just, so this is I to j basically. So this is common for all. So we will consider, okay, so let r be initially 1. So R will be initially, R varies from 2 to 5. So let R be 2 first. So this will be OBST of 2 to 1 plus OBST from 3 to 5. Okay, plus this constant, let's put it as, so this PK. Okay, so summation PK. So let's try to calculate it also, and if we calculate P2 plus P3 plus P4 plus P5, it comes out to be 0.68. okay, so other, if I make R is equal to 3, so this will be OBST, so 2 to 2 plus OBST, so it will be, because R is now 3, so it will become 4 to 5. Okay, plus 0.68. okay, so let's move little further. So we will have now, when R is equal to 4, so this will be OBST 2 comma 3 plus OBST, so 4, so it will be 5 comma 5 plus 0.68. And finally when R is 5, so this will be OBST 2 to 4 plus OBST, so it will be now R plus 1, so it becomes 6 till 5 plus 0.68. okay, so now we see what we are trying to find, OBST 2 comma 5. So we see 2 comma 5, this one we are trying to find. So we have everything before that we will already have calculated, because we go from bottom to top, bottom up. Okay, so OBST 2 comma 1, as we said that, okay, when j is I minus 1, this becomes 0. So let's use some different color. Okay, so we will use now, let's say, a black color. So this one is 0. So this one becomes a 0, and OBST 3 comma 5, if we see, this is 0.8. okay, so this one is 0.8. so here we will just write this 0.8. okay, this one is now 2 comma 2, is we have to calculate from there, we have to look up in the table, and 2 comma 2 is 0.18. okay, so this one is 0.18 plus OBST 4 comma 5, so that is 0.35. this one becomes 2 comma 3, so 0.56 plus 5 comma 5, which is 0.25. and finally the last one, if we see, so this is, again this one is 0, so 2 comma 4 is 0.66. so what happens here, this one is common, so we are not calculating. okay, so this is 0.8, so this is 0.51. okay, so this one becomes 0.5, so okay, something like that. This one becomes 56, 66, 76, 81, so 0.81. this becomes 0.66, and this becomes 0.53. okay, so we see that this is the minimum, so which means I am taking the third element as the R is equal to 3 as the root for the optimal binary tree construction. And basically, so I was not adding this cost, so now it will become 0.53 plus this 0.68 is equal to 1.21, and which we see is the optimal value for 2 to 5. So here if we see, this is 1.21. So this is the way we were doing the calculation. So I made one calculation so that it becomes easier for you to understand. So one thing that we have not done here is that we here assume that okay, for construction we only have searches that are from the elements of the binary search tree. So we have taken only probabilities for that, but even there can be searches or occurrences of numbers which are not present in the search list. So we can extend it very easily for that, but this program basically tells us the use of dynamic programming to solve the problem of optimal binary search tree construction. And we see here that we, in making use of 2,5, we made a use of lot of recurrence relations. So we had overlapping sub problems, and then basically 2,7 will also have all the sub problems that we solve for 2,5. So we have overlapping sub problem and optimal substructure. So this was about dynamic programming solution for optimal binary search tree. So I hope you understand this, and if you like this video, please subscribe to my YouTube channel.